Geometric calibration and shape refinement for 3D reconstruction. 3D reconstruction is an interesting computer vision problem which finds its applications in many different areas. There are different methods of 3D reconstruction known in computer vision. Structure from motion, structured light stereo, binocular stereo, photometric stereo, etc. Most of these methods work based on either the principle of ray triangulation or the principle of photometry. Examples of triangulation-based methods include binocular stereo, structured light stereo, and structure from motion. Photometry-based methods include photometric stereo and shape from shading. Together, this is a broad area of research from which, in the thesis, we have chosen three important problems to investigate, namely robust and efficient large-scale rotation averaging, accuracy analysis of structured light stereo depth cameras, and a fusion of structured light stereo with photometric stereo. Problem 1. Robust and efficient relative rotation averaging. Relative rotation averaging finds its application in the context of structure from motion, or SFM in short. SFM is a method of 3D reconstruction from photographs based on multi-view triangulation. A class of SFM methods perform the 3D reconstruction in three phases: estimation of camera orientations, estimation of camera positions, and estimation of scene geometry. We concentrate in the first phase, that is estimation of camera orientations. If images from two cameras have sufficient overlap, we can estimate the relative orientation or relative rotation between them using feature correspondences and epipolar geometry. Subsequently, we have to estimate the absolute orientations of all the cameras from a set of estimated relative orientations, which is known as relative rotation averaging. Estimated relative rotations are always corrupted with measurement noise and outliers. In spite of that, we want our method of relative rotation averaging to be robust to such outliers, accurate, and computationally very efficient. The problem of relative rotation averaging can be described with the graph on the screen. Each circular node represents a camera with an unknown rotation. The edges represent estimated relative rotations. The task is to find the absolute rotations of the cameras from a given set of relative rotations. Both absolute and relative rotations can be represented as 3 by 3 orthonormal matrices with positive determinant. If the absolute rotations of camera I and J are Ri and Rj respectively, then the relative rotation between them should be Rj Ri inverse. We formulate the relative rotation averaging as an optimization problem where we minimize the sum of discrepancies between the observed relative rotations Rij and the relative rotation given by Rj Ri inverse for all the edges. The distance between two rotations is measured by the geodesic distance in the manifold of 3D rotations. The robustness of the solution to the outliers depends on the choice of the loss function rho. To solve this optimization problem, we exploit the Lie group structure of 3D rotations. We reduce the problem into an iteratively reweighted nonlinear least squares, and in each iteration we carry out a quasi-Newton optimization. Experimental results suggest that our method is more accurate and faster than the existing state-of-the-art methods with a significant margin. It is our pride that our method is adopted by the researchers from different research groups across the globe for accurate and efficient solution for large-scale structure from motion problems. Our method is also implemented in several SFM libraries like OpenMVG, Thea, and Rigard 3D. Problem 2. Accuracy of structured light stereo, modeling and its applications. We saw from the working principle of a structured light stereo depth camera that the noise or inaccuracy in depth estimation increases quadratically with the distance of objects from the camera. We also verify this noise model with thorough experiments. Further, we propose how to exploit this noise model to enhance the performance of different applications involving a structured light stereo depth camera. Application 1. Depth map denoising. We propose a simple depth adaptive bilateral filter which automatically tunes the amount of smoothing based on the distance of objects, that is, based on the expected amount of noise. Application 2. Scan merging. We propose a weighted volumetric merging of scans where scan points are weighted depending on their distances from the scanner. Such a merging scheme preserves object details better than unweighted merging. Application 3. Plane segmentation. We propose a real-time method for extracting planar regions from disparity maps, exploiting our knowledge about the noise in a structured light stereo depth camera. We also propose how to deal with the noise characteristics of such cameras in a pipeline for 3D reconstruction. Here are some reconstructions from our pipeline. A 50 cm high C.V. Raman bust situated in Material Research Center, Indian Institute of Science. My old hostel room in Indian Institute of Science. A model combat aircraft situated in the Department of Aerospace Engineering, IISc. Life-size statue of Mahatma Gandhi situated in Sabarmati Ashram, Ahmedabad. Problem 3. A fusion of photometry and structured light stereo. Commercial structured light stereo depth cameras have very low depth resolution and they are not able to capture the fine scale details of objects. However, infrared cameras of such devices are of substantially higher resolution. Therefore, we can estimate 3D structure of objects from the intensity images captured by the infrared cameras of such devices using photometric stereo. Photometric stereo based methods can capture the fine scale details of the objects very well. However, photometric stereo as a standalone method for 3D reconstruction has some drawbacks. Firstly, it requires a precise calibration of lighting setup which is tedious. Secondly, 3D reconstructions obtained using photometric stereo often suffers from coarse level deformations. On the other hand, structured light stereo cameras are quite accurate at the coarse level while they cannot preserve the fine scale details. Exploiting this complementarity of photometric stereo and structured light stereo, we propose a fusion to take advantages of both the methods. Our method does not suffer from coarse deformations and is also able to preserve the fine scale details of objects. We also do not need to perform a tedious calibration of the lighting setup since we estimate the lighting automatically using the coarse depth maps obtained with structured light stereo. We shall finish this brief presentation with some reconstruction results with our fusion approach. A 25 cm high terracotta plaque. On the left is the raw scan and on the right is our refinement. Another 25 cm high terracotta plaque of Rabindranath Tagore. On the left, scan obtained with a Kinect, and on the right, our refinement. A 20 centimeter diameter carved wooden plate. On the left, 3D reconstruction, and on the right, estimated albedo map. A pair of shoes and some detailed views. A woolen jacket, 3D reconstruction and estimated albedo map. A pair of shorts. A woolen sweater. Some geological samples, 3D structure and albedo map. A multi-view reconstruction of a terracotta figurine of Ganesh. Another multi-view reconstruction of a terracotta figurine of Buddha. On the left, reconstruction with raw scans, and on the right, our refinement result. Thank you. My thesis is available in openthesis.org as well as in ResearchGate.